Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah. Let us solve some exercises about section 11.7. This section is a review of all what we studied about series from 11.2 to 11.6. So you need to study uh, the previous sections before starting or looking to these exercises. The question is test the series for convergence or divergence. We will follow the strategy we used in the previous section, in the previous video, the same section, but the video before this, in which we illustrated 22 examples. So I try to, this is a polynomial over polynomial. So I will think of a Bn comparison test. N square over n cube, these are the highest powers. When I divide them, I get 1 over n. So I have a minus and a plus here. 1 over n is divergent, the harmonic series, the divergent harmonic series. And I cannot prove that this is less than this, is greater than this, because I have plus in the denominator. So I will use the limit comparison test. To use the limit comparison test, I find the limit of an divided by bn when n goes to infinity. When I multiply n times these two terms, the highest power would be n cube. The highest power here is n cube, so the limit is 1. 1 is greater than 0. So by limit comparison test, the series diverges because 1 over n diverges, so it's divergent also by the limit comparison test. Here I have the same series, but I have negative 1 to the power n. So if I take the absolute value, I'll get this series, and I know it's divergent. So this series is not absolutely convergent, okay? But it could be conditionally convergent. The series itself could be convergent if I try to use the alternating series test, because I have negative 1 to the power n. So to use the alternating series test, this is Bn now, okay, and all of it is An. So the two conditions, I have to check the two conditions of the alternating series test. Limit of Bn when n goes to infinity should be 0, and it is 0 because the highest power over the highest power will give you 1 over n. So the limit is 0, so this condition is okay. And I need to prove that Bn is decreasing. And for that, I will find the derivative of this function using the quotient rule. Derivative of the numerator is 2x. Derivative of the denominator is 3x squared. I can take x as a common factor. So I'll have 2x cubed plus 2. I take x from x squared as a common factor, so I still have 3x only. So 3x times x squared is 3x cubed, and minus 3x times negative 1 is positive 3x. So f prime is equal to, now 2x cubed minus 3x cubed is negative x cubed, and I have negative x cubed plus 3x plus 2. I took x as a common factor. Okay. X cube plus 1 x square minus 1 and over x cube plus 2 to the power 2. Okay, derivative is 2x 3x square. I wanted to make sure that my answer is okay. Yeah, it's okay. So now f prime of x for x greater than or equal to 1, we need it to be less than 0. I can use the calculator to find the zeros of this polynomial. Negative x cube plus 3x plus 2. It has 2 and negative 1. So I can write it. Yeah, factoring this is not easy. 2 is a 0, so I will divide by x minus 2, long division. Change the sign and add. I have negative 2x squared plus 3x plus 2. So negative 2x. Change the signs. So negative x plus 2. So this is just negative 1. Okay, so if I change the signs and add, I'll get 0. So I have x times x minus 2 times, this is x squared plus 2x plus 1. If I take negative as a common factor, it would be x squared plus 2x plus 1 over x cubed plus 2 to the power 2. So f prime would be negative x times x minus 2 times x squared plus 2x plus 1 is just x plus 1 to the power 2. It's the perfect square. So it wasn't really easy to factor this polynomial, okay? And now uh, f prime has some zeros. 0 is a 0, negative 1 is a 0, 2 is a 0. The important one for us is 2, and we need to check what if for x is greater than 2. If I choose a number 2 greater than 2, okay, greater than 2. If I take 2, it would be 0. I can say that is less than and put a equality here also. So 3, choose 3. Positive, positive, positive. You have negative. So f prime is negative for x greater than 2. Okay. This means that f is decreasing for x greater than 2 or equal to 2 or 2. Okay. If it is greater than 2, let me do it like this. So the two conditions are satisfied. So summation an from 2 to infinity, okay, is convergent by alternating series test. And hence, if you add a number, it's also convergent. So proving decreasing here, that it's decreasing, it needs some effort just to make sure that f prime is less than 0. So at the end, this series is conditionally convergent. Here I have e to the power n, so I can immediately use the ratio test. So this is en plus 1 over n plus 1 square multiplied by n square over en, the reciprocal of en. And now some cancellations. This with this, I'll have e. So I'll get e times n square over n plus 1 square. Well, the limit of n square over n plus 1 square when n goes to infinity is 1 because the highest power is n square in numerator and denominator. So 1 times e would be e, and e is greater than 1. So by ratio test, series is divergent because L is greater than 1. You may try to find the limit here of an. You find that infinity over infinity. So to find the limit, I use L'Hopital's rule. Infinity over infinity. So using L'Hopital's rule, the derivative of ex as ex and here 2x. Again, I get infinity over infinity, so I use L'Hopital's rule again. And now e to the power infinity is infinity over 2 is infinity. So limit is infinity. So here I can say that series is divergent, but this time by using test for divergence. Both methods are correct. Here I have nth power, so I will immediately think of the root test. If I take the nth root of absolute value of an, I'll get n square over 1 plus n to the power 3. Because I can write this n square over 1 plus n cube all to the power n. Remember that x to the power a all to the power b is x to the power a times b. And now if I take the limit when n goes to infinity of n square over 1 plus n to the power 3, the highest power in the numerator and the highest power in the denominator, the term with the highest power. So it would be 1 over n, and the limit is 0, which is less than 1. So by root test, series is convergent. It's nice if you stop a little here and try to solve this question by yourself. It's a review for you. Well, I have 1 over n ln n. If I want to compare it with 1 over n square root of ln n is greater than n. So 1 over this would be less than 1 over n, but 1 over n is divergent. And I have ln here, so using the limit comparison test may be not straightforward. But we solved similar problems like this using integral test in section 11.3. So let me consider the function f of x equals 1 over x square root of ln x. and this function is positive, continuous from 2 to infinity, because x starts from 2, len 2, I have no problems with continuity, or it's positive. But now I need to prove that it is decreasing, so I need to find f prime of x. And for finding f prime, I'll use the formula, uh, the formula that derivative of 1 over u is negative u prime over u square. So I'll have x square times ln x, and I'll have negative the derivative. Derivative of x is 1. I'll use the product rule, plus x times derivative of square root of ln x is 1 over 2 square root of ln x times the derivative of ln x, which is 1 over x. So x cancels with x. And to get rid of square root 2 square root of ln x, I will multiply by 2 times square root of ln x. So I will have x squared times 2, and ln x I'll have it to the power 3 over 2, power 1 and power half here. And now I have a minus sign, and I'll get here 2 square root of ln x times square root of ln x, plus, if I multiply this by 2 times square root of ln x, I'll just get 1. And we can see that the denominator is always positive, and the numerator is always negative. Because this is always positive when x is greater than or equal to 2. So f prime is less than 0 for x greater than or equal to 2. This means that I can talk about the improper integral from 2 to infinity of 1 over x square root of ln x. And by definition, this is the limit when t approaches infinity of this integral. Well, yes, the integral of the function f of x. And to find the integral of 1 over x times square root of ln x, we take u equals ln x, then du would be 1 over x dx, and the integral would be 1 over square root of u du. And this would be u to the power negative half du. And the integral would be u to the power half over half, or times u, and u is ln x, so in fact this would be the integral. So this is equal to the limit of 2 square root of ln x from 2 to t. And I'll have 2 square root of ln t minus 2 square root of ln 2. Ln infinity is infinity, square root of infinity is infinity, 2 times infinity is infinity, infinity minus a number is infinity. So the improper integral diverges. So summation an also diverges by the integral test. So this is also an example about the integral test. I have powers, factorials, so immediately I'll use the ratio test. Let me write it. pi to the power 2 times n plus 1 pi to the power 2n. Now let us concentrate to find what are the cancellations here. Well, this one is 2n plus 2 factorial. So it's 2n plus 2 times 2n plus 1 times 2n factorial. And these two will be cancelled. And this is pi to the power 2n times pi to the power 2, 2 times 1. So I can cancel these two and I'll have pi square up. And I can cancel these two and I'll have negative 1 here. So let us see what do we get. Negative 1 will disappear with the absolute value. I'll have pi square over 2n plus 2 times 2n plus 1. And when I take the limit when n goes to infinity, this quantity will be pi square over infinity, which is 0. And 0 is less than 1. So by ratio test series is absolutely convergent. Of course, if you say convergent, that's also okay. But the root test and the ratio test tell us immediately that the series is absolutely convergent if L is less than 1. You can use the integral test to test the divergence and convergence of this series. But I will use the ratio test here. And first I will write it as summation n square over e n cube. So an plus 1 over an would be n plus 1 square over e to the power n plus 1 cube times en cube over n square. Now I need to expand n plus 1 to the power 3. There is no need of the absolute value. I have e to the power n cube over e to the power n cube plus 3n square plus 3n plus 1 if you expand n plus 1 cube. So I can cancel en cube with en cube and I'll get n plus 1 square over n square times 1 over e to the power 3n square plus 3n plus 1. Now if I replace n by infinity, limit n, if I find the limit when n goes to infinity, the limit of n plus 1 square over n square is 1, and the limit of 1 over e to the power would be 1 over e to the power infinity, well, 1 over infinity, which is 0, and 0 is less than 1. So by ratio test, summation an is absolutely convergent. Here we have a sum of two series. Summation 1 over n cube is a convergent P series because P is 3, which is greater than 1. And summation 1 over 3 to the power n is a convergent geometric series since R is 1 over 3 less than 1. So sum of two convergent series is convergent. So summation an is convergent. Here we have a problem with this series because sine 2n sometimes positive, sometimes negative. It's not alternating. If you replace n by 1, you find that sine 2 is positive, sine 3 is positive, sine 4 is negative, sine 5 is negative, sine 6 is negative, and so on. Okay, you don't know when it becomes negative and when it becomes positive. So it's not alternating. You cannot use alternating series test. And it is not positive. The terms are not positive. So you cannot use comparison or limit comparison or, of course, integral is not possible here. It is not easy to evaluate the integral. So what we do, we use the absolute value. We talk about the absolute value of sine 2n over 1 plus 2n. And when we consider the absolute value of sine 2n will be like this. We don't know whether it's positive or negative, so we leave the absolute value, but this is always positive. But now I can write this less than 1 over 1 plus 2n, less than or equal, because any sine 2n is always less between -1 and 1. So it's less than or equal to 1. And I still can write this less than 1 over 2 to the power n and remove the 1 from the denominator, because 1 plus 2 to the power n is greater than 2 to the power n. So 1 over would be less than. And summation 1 over 2 to the power n is a convergent geometric series, because r is half and it is less than 1. So because of this, and by direct comparison test, then summation absolute value of sine 2n over 1 plus 2n is convergent. And because this is convergent, then summation an without absolute value is absolutely convergent. So the series is absolutely convergent. Here we can write it like this. 2 to the power k minus 1, 2 to the power -1 times 2 to the power k, 3 to the power 1 times 3 to the power k over k to the power k. So 3 over 2, because this is 2 to the power -1, and I have 2 to the power k times 3 to the power k. This is 2 times 3 all to the power k and k to the power k. So I can write it as 6 over k to the power k. And because of this, I can use the nth root. Okay, I use the root test. Let me say a to the power ak here. Okay, so if I take the kth root of a to the power k, forget about 3 over 2. So I will have 6 over k. Okay, 6 over k. A k will be removed. I'll have 6 over k. And when I take k, when limit k goes to infinity, would be 6 over infinity, which is 0. And this is less than 1. So by root test, summation 6 over k to the power k is absolutely convergent. Then a multiple of this series would be also convergent. Okay, a multiple of a convergent is a convergent. Here I have alternating series, so I will use the alternating series test. I can think of trying to find the limit of uh, ln over square root of n, but I'll just want to use the alternating series test. I'll have to use L'Hopital's rule. Let us do it, why not? Let us find the limit of ln n over square root of n. This will give you infinity over infinity. So let us use L'Hopital's. Derivative of ln x is 1 over x. Derivative of square root of x is 1 over 2 square root of x. Now this is 1 over x, so x will be here. And I have 2 here, square root of x. Square root of x will go up if you simplify this. You can simplify it if you like by writing it 1 over x divided by 1 over 2 square root of x, and then 1 over x times 2 square root of x. Yeah, so this 2 will not be here. It will be up because 1 over, okay? So I'll have 2 square root of x over x, or 2 over square root of x, 1 minus half, so the limit is 0. Okay, so it's not divergent using the test for divergence. The absolute value is not divergent. So let me use the alternating series test. To use the alternating series test, Bn, this is Bn. Okay, I proved here. That's nice. We proved that the limit of Bn when n goes to infinity is 0. Okay, and that's the answer. We used L'Hopital and we proved it's 0. Good. For the second part, I need to prove that it's decreasing. So f of x as a function, ln x over square root of x, and f prime of x would be quotient rule. Derivative of ln x is 1 over x. Ln x times derivative of square root of x, which is 1 over 2 square root of x. Let me multiply by 2 square root of x over 2 square root of x to get rid of the denominator in the numerator. So I'll have 2 here, and 1 plus half is 3 over 2. So I'll have x to the power 3 over 2. And pay attention to this. This is already square root of x over x. So it is 1 over square root of x. When you multiply by 2 square root of x, you will just get 2. Okay? Or you can multiply square root of x times square root of x. X cancels with x and you get the 2. Minus 2 square root of x cancels with 2 square root of x, and I get ln x. Now, for x greater than, let us find exactly what is the 0 of the numerator. The denominator, the 0 is 0, but 0 is not in our interest because we need from 1 to infinity. So let me find the 0 of 2 minus ln x. So 2 will be equal to ln x, or x would be equal to e square. Okay, so that's the 0 of the numerator. E square is 7.4, approximately 7.4. Okay, so I can say that f prime of x is less than 0 for x greater than 8 or equal to 8. If you put 8, 2 minus ln 8 would be negative. So f is decreasing for n greater than or equal to 8. This means that summation an from 8 to infinity is convergent by alternating series test, and hence summation from 1 to infinity is also convergent. Whenever you add any finite number of terms to a convergent series, it would be convergent. Factorial immediately the ratio test. Cancel this with this. I'll have n plus 1. And this is e to the power n square plus 2n plus 1. So en square will be cancelled with en square, and I will have n plus 1 up over e to the power 2n plus 1. All right. Now I need to find the limit of this. When n goes to infinity, I have infinity over infinity. So I switch to x functions and use L'Hopital's. Infinity over infinity, so I use L'Hopital's. Limit of x is 1. Limit of e to x plus 1 is e to the power 2x plus 1 times the derivative of 2x plus 1, which is 2. Now if you replace x by infinity, 1 over infinity is 0. So the limit is 0. It is less than 1. So by ratio test, series is absolutely convergent. N square 5 to the power n ratio test. There is no need for the absolute value. All are positive. I can cancel this with this. I'll have 5 here. And now this would be equal to I'll have here n square plus 2n plus 1 plus 1, so that's plus 2 over n square plus 1 times 1 over 5. And the limit of this quantity is 1 because n square over n square is 1. So when n goes to infinity, this quantity will go to 1 over 5, which is less than 1. So by ratio test, series is absolutely convergent. Well, I can solve this one in 2 ways. All the terms are positive. So notice that 3 to the power k plus 4 to the power k is less than 4 to the power k plus 4 to the power k because 3 is less than 4. And this is 2 times 4 to the power k. So 1 over 3 to the power k plus 4 to the power k would be greater than 1 over 2 times 4 to the power k. And then 5 to the power k over 3 to the power k plus 4 to the power k would be greater than 5 over k, and this is in fact 1 over 2 times 5 over 4 to the power k, and summation 5 over 4 to the power k times half, if you like, is a multiple of a divergent geometric series. Since R is 5 over 4 and it's greater than 1. So by direct comparison test, because I used the comparison test here, summation AN is divergent, because I proved that AN is greater than BN, where summation BN is divergent. Or if you try to find the limits of 5 to the power k over 3 to the power k plus 4 to the power k when k goes to infinity, and if you divide by the highest power, and let us say divide by 5 to the power k up and down, so I'll have 1 here, and here 3 over 5 to the power k, and here 4 over 5 to the power k. And or yeah, you can do this, okay? Or you can divide by 4 to the power k if you like. Both are correct. Both are possible. If I divide by 4 to the power k, I have 5 over 4 here to the power k. And here 3 over 4 to the power k. And here 4 over k over 4 over k, that's 1. And now what is the limit of 5 over 4 to the power k? The limit is infinity because 5 over 4 is greater than 1. While 3 over 4 to the power k, the limit is 0 because 3 over 4 is less than 1. We studied this in the beginning of chapter 11. Limit r to the power n. When r is less than 1, the limit is 0. When r is greater than 1, the limit is infinity. So the limit is infinity. So by test for divergence, series diverges. So here I proved that the limit of AN immediately is not 0 or does not exist, is infinity. So I can use the direct comparison test or test for divergence. I hope these exercises are enough for you to understand everything about series.